Okay, in this second half of chapter 18, we're going to start off the second law of thermodynamics, and we try to derive this law to introduce another important thermodynamic state function. Let's look at the second law of thermodynamics again. We understand for any spontaneous process, the entropy change of the universe must be greater than zero. That means entropy change of a system plus the entropy change of surroundings together must be greater than zero. Not one of them. Should be both combined. In our last lecture, we have done some calculation about entropy. We even introduced the entropy to the standard state condition. In this way, so we can put the standard entropy formation, and we can combine this standard entropy of formation with the Hess's law so that we can actually calculate the delta S0 of the reaction. Standard entropy of the reaction is also equally important as the delta HL0 of the reaction, standard heat of the reaction, because that gives us a certain point of view to understand what kind of driving force that can put this reaction forward. However, there's still unfinished business in the second law of thermodynamics. When we look at this equation again, we realize not only do we have to study the delta S of the system in order to predict a spontaneous process, we also have to study delta S of the surroundings. The reason is when we add these two delta S's combined together, we can only be able to predict whether this process is spontaneous. If we have to study the surroundings, what's the point for us to study system? Because we want to single out something we call the system for us to study so that we can get the problem done, get the problem solved, so we do not have to get ourselves too much into the surroundings. With that thought in mind, we have to find a replacement of delta S of the surrounding using something that we can measure from the system. That something here is the delta H of the system, entropy change of the system. If you talk about a reaction, that would be the heat of the reaction. Let's see how we can relate this delta S of surroundings with the heat of the reaction. Say if we have an exothermic reaction where the delta H of the reaction is less than zero. Since delta H of the reaction is negative, meaning that the system loses heat and the heat is being accepted or absorbed by surroundings. There's only two ways for a system to absorb heat. One, the temperature increases as heat is absorbed. Or, if temperature doesn't increase, then the surroundings must undergoing a state change, in which the delta S also increases as a result. What I'm trying to say here is, no matter which way the surroundings accept the heats, either raising the temperature or undergoing the state change, the delta S of the surrounding is greater than zero. The surrounding undergoes a state where it has more entropy. Now, from this discussion, we realize we can relate the heat of a reaction with the delta S of surroundings. There are two types of reaction as we discussed. One type is exothermic, the other one is endothermic. So now let's see if we come up with similar conclusion from our discussion that we had before. If a reaction is endothermic, delta H reaction must be 0, greater than 0. Since it's greater than 0, reaction or the system absorbs heat, the heat comes from the surroundings. In other words, surrounding releases heat, loses heat. Two consequences for surrounding after surrounding loses heat. One, temperatures may be dropped down. Or, if temperature doesn't change, the surrounding undergoes the change of state. For example, from a gas to liquid, from liquid to solid. Either way, we start to see the decrease in the delta S of the surroundings. Remember the cases we have discussed about the entropy prediction. Delta S increases as the temperature increases, and entropy of solid is the least, while the entropy of gas is the greatest. So either way, we'll find out that we can have delta H of a reaction related with the delta S of surroundings. All right. So it seems like if delta H is less than 0, delta S is be greater than 0, and the delta H reaction is greater than 0, delta S is less than 0. And it is kind of difficult for us to make the mathematical relation, but it will be much better if we can put a negative sign in front of a delta S. In this way, delta H reaction and a negative delta S of surroundings have the same sign. They either both less than 0 or they both greater than 0. In this way, we can say delta H of the reaction is directly proportional to negative delta S of surroundings. Okay, our next goal here is try to replace this sign of direct proportional to equal. Before we can do this, let's check out the units of this delta H and the delta S. We realize delta H has a unit of joule, although kilojoules is more common. Delta S here has a unit of joule per Kelvin. So this side, it has a unit of joule, and on the right-hand side, it is a joule per Kelvin. What function should we add to the other side, one side of the equation, so that both sides has the same unit, for example, joule? And you may see it, we can multiply negative T, negative delta S of surroundings by temperature, because temperature has the unit of Kelvin. So now we have established an equation that's a relate, mathematical equation by the way, that is relate the delta H of the system with the delta S of the surroundings. Delta H of system equals to negative T times delta S of surroundings. Let's go back again to the second law of thermodynamics. Delta S of universe equals to delta S of surroundings plus delta S of system greater than 0. Now this time, we are going to multiply negative T on all the sides, left, middle, and right. In this way, we have negative T times delta S of universe that equals to negative T times delta S of surroundings plus negative T times delta S of system, okay, plus and negative, so we have a minus T times delta S of surrounding system. Remember, we can times negative t. So that is a negative sign in front of it. So what used to be the greater sign now has switched to the less sign. So it's going to be less than 0. Remember that we have just discussed we can replace negative t times delta S of surroundings with delta H of the system. Then the second law of thermodynamics becomes this: delta H of the system minus t times delta S of the system less than 0. That is big. That is a milestone. Why? Because now we can just concentrate our measurement on the system so that it will give us a clue to determine whether this reaction is going to be spontaneous. Because once we figure out what the delta H is, delta S is, and what the temperature the system is at, with this particular calculation, we should be able to predict whether this process is spontaneous. As long as the subtraction gives us 0, less than 0 value, or negative value, we got a spontaneous process. So that the delta H minus T times delta S is big. And this is the equation that we can use to describe, to represent the second law of thermodynamics, the law that tells us how we are able to predict a spontaneous process. But you notice that we have a delta H and delta S in that equation. That is not a good enough mathematical representation. So that is why another state function is proposed or defined. It is called free energy, G. G also stands for Gibbs. Okay? So we call this G as a Gibbs free energy. It's defined as an H minus T times S. Kind of like a delta H, the definition of delta H with a certain condition. And of course, delta G under the condition of constant temperature and pressure, it is equal to delta H minus T times delta S. I just want you guys to know this. We have got the delta H minus T times delta S here, and the delta H minus T times delta S here. And according to that equation, we also have something on the left, which is T times delta S of universe. And we do have something that's on the left that we call delta G, the change in Gibbs free energy. And of course, we can make delta G of the system equals to negative T times delta S of the universe. In this way, we suddenly realize we do not have to worry about the delta S of the surroundings. We do not have to worry about the delta S of the universe, because now we got the delta S of surroundings as well as that of the universe all converted back to some property of the system, which we can measure. So the introduction of the free energy actually provides the mathematical support for us to understand the second law of thermodynamics much, much better. Because it's very simplified. It's very simple. The sign of delta G of the system actually tells us what or how second law of thermodynamics works. Remember, in order for us to have the spontaneous process, delta H minus T times delta S must be less than 0, and also according to that, the delta G must be less than 0. So when it's less than 0, the reaction is spontaneous. If If delta G of the system greater than 0, the reaction is not spontaneous. In other words, the reverse reaction becomes spontaneous. If delta G of the system equals to 0, now we understand that the reaction is at equilibrium. That is in the dynamic balance. So a few more things I want you guys to understand better by highlighting these. So what is delta G of system really stands for? The delta G of system stands for this. And what's the function of delta G of the system? To a certain extent, we actually do not care what the value of delta G of system is. All we care is what sign that the delta G has. Is that negative, positive, or 0? If it is negative, the reaction is spontaneous. Positive, the reverse reaction is spontaneous. Gibbs free energy, G, actually is first proposed by a Yale professor, Gibbs, J. Willard Gibbs. My understanding is if he could live a few more years longer, say till 1910, he would have got a Nobel Prize in physics, because his definition of free energy make thermodynamics looking so good. Beautiful and simple mathematical equation explains some complicated physics phenomena. G, the free energy, is a state function, as I already said, because that is why we put a capitalized G to represent it. Remember, for thermochemistry, if we have a function that is a state function, the symbol must be capitalized or must be in uppercase. Just like H, its component has no absolute value, G does not have that absolute value either. And by having G, the free energy, it becomes a single measure by combining this delta S of system and the delta S of surroundings. That based only on the information we obtain from the system. Meaning we do not have to worry about what's going on in the surroundings. We do not have to worry about what's going on in the universe, which is these two combined. All you have to do is focus on system. That is a mathematical guideline. And if we follow in science the mathematical guideline, we will get answer. We will get the solution. That is why mathematics becomes so important in science, because math is a guideline for us to get the results. If math proves the results are true, we do not have to worry about, we do not have even to bother to prove that it's wrong anymore. Since G has no absolute value, so we are interested in the change of free energy, which is delta G. Delta G is an indirect measure of spontaneity of the process. Of course, here are the catches. At a constant pressure and a constant temperature. We must have these two conditions in order to make delta G equals to delta H minus T times delta S. The sign of delta G demonstrates the reaction spontaneity. That means if you have delta G greater than 0, the process is not spontaneous. The reverse one actually is. If we want a spontaneous process, delta G must be less than 0. One other thing I'd like to point out, if you do not realize the word of indirect in this statement. Indirect means we cannot measure it directly. the delta G actually is not something we can measure directly from the experiment. We can calculate it, we can derive it, but we can never measure it from our instrument. We can measure delta H, we can measure delta S even, but we cannot measure delta G. We can only calculate delta G by laying out the delta H, delta S in the way indicated by the math, delta H minus T times delta S. So one more time, I'd like to emphasize how important this subtraction is for second law of thermodynamics. If we want to have the spontaneous process, delta H of the system minus T times delta S of the system must be less than 0. Now we understand that the delta H minus T times delta S is the representation of second law of thermodynamics. Since it's a math equation, we can actually play a little bit manipulation. So say we can have a delta H plus T times negative delta S. Why I'm doing this? Because I want to isolate T out, because T is a temperature. In the unit of Kelvin, T is always positive. And we know delta H could have positive or negative depending on type of the reaction. Delta S could be positive or negative depending on just how chaotic or the randomness of the reaction reaches. So we can play combination. And we find out that there are 4 combinations. So let's lay them out and see what can we learn from those combinations. Our first combination is that the delta H is less than 0, delta S is greater than 0. Remember, both delta H and delta S are the measurement from the system, a state function of the system, of the reaction. With a positive delta S, negative delta S must be less than 0. And if you look at this equation here, delta H is negative. Negative T times delta S is negative. Multiplied by something positive, still one of negative. Negative plus negative, delta G has to be negative. What can we learn from this simple math? The simple math is, regardless of what temperature that is, delta G is always negative. Meaning, this process is spontaneous regardless what temperature this process is at. In other words, this reaction or this process is independent of temperature. If a reaction is set for spontaneous, it is spontaneous all the way, no matter what temperature. Come to think of it, that makes sense. Because remember, if delta S of the reaction is positive here, the entropy increases. Entropy of the reaction increases. From the discussion of delta H of the system represent the delta S of surroundings. Delta H is less than 0. System loses energy, surrounding gains energy, temperature rise on the surroundings, delta S of surrounding increases. Delta S of surrounding increases, delta S of systems increases. We got yourself a spontaneous process. A very good example for this type of combination is the decomposition of the reaction, decomposition reaction of NO2. How do we know this is a spontaneous reaction that is independent of temperature? Because this decomposition reaction releases heat. It's exothermic. By looking at the reaction start with a less amount of gas yields ending up with the more amount of gas particles. That is standard case for increasing of entropy. If you haven't realized, I'd like to tell you that NO2 is one of the major air pollutants in this country. This reaction actually tells us NO2 can be decomposed into N2 and O2. According to thermodynamics, it's going to happen. This reaction is plausible. But why we still have this problem of NO2 in our air? Because although this reaction is spontaneous, but it is not instantaneous. This reaction is not going to happen anytime soon. Why? Activation energy of this reaction is too high. So that is the reason why there's still a group of scientists working on a catalyst to make this reaction happen. So we can put this catalyst in our exhaust system of the vehicle. In this way, we do not have to worry about NO2, so all we have is N2 and O2. That definitely makes our environment much better in this way. Our second scenario, our second combination here is delta H is greater than 0, delta S is less than 0. From our discussion about the delta H to the delta S of the surrounding, so we realize if the reaction absorbs energy from the surroundings, delta S of surrounding decreases. We have a delta S of surrounding decreases, delta S of the system decreases, the delta S of the universe decreases less than 0, meaning this process is not spontaneous. Of course, let's see how our math tells us. If delta S is less than 0, negative delta S must be positive. Okay, negative delta S is positive, multiplied T is positive, one thing up, one side of positive. If delta H is positive, delta G is always positive. So that confirms our analysis. This reaction is non-spontaneous, no matter what temperature this reaction is at. In other words, this is another case where we see it is totally independent of temperature. A very good example will be the reaction of oxygen to form ozone. This is a non-spontaneous process. But you may be puzzled why we have ozone. Everybody knows how important ozone layer is in our atmosphere to protect us from the radiation of UV light. Why we still have O3 layer, even though we understand the formation for O3 from O2 is not spontaneous, meaning it's not going to happen all by itself. Why do we still have the O3? Because there's continuous external energy input to make this reaction to take place. What's the source? UV light, UV radiation from the sunlight. But what is even more amazingly is, in order to have O3 decomposes down to the O2 without those free ions or anything, O3 needs to absorb another part of UV light to get themselves activated. so that the reaction can take place. It decomposes down to the O2. Formation of O3 requires more energetic spectrum of UV light. Decomposes of O3 requires less energetic spectrum of UV light. So the formation and decomposition of O3 actually provides a perfect block of UV light by absorbing it. So I just hope that with this discussion, we understand that why we have O3 and how O3 can protect us from the UV radiation. All right, so let's go back to the chemistry here. So from these first two cases or scenarios, we realize that we do have a certain combinations of delta H and delta S that shows independence of temperature. And when we read out these two combinations, we realize that the delta H and the delta S must have different sign. If delta H is negative, delta S must be positive. If delta H is positive, delta S must be negative. All right. What about the other two combinations in which both delta H and the delta S have the same sign? Our first combination here, or our third combination of these four, is delta H less than 0, delta S is less than 0. We got yourself again exothermic reaction, but this reaction has its delta S decreases. All right, if delta S is less than 0, we understand the negative delta S must be positive. So we got this term positive, this term negative. And I'd like to remind you, the common unit for delta H is kilojoules. The common unit for delta S is joules per Kelvin. Joules times the temperature in Kelvin, so that we can have joules, right? Joules per Kelvin times Kelvin, so we have joules. Kilojoules to begin with, joules that we have the increase as temperature increases. So we realize that at the lower temperature, we could have negative sign for delta G. That means this process is spontaneous at a lower temperature. However, if temperatures are high enough that make T times negative delta S more positive, which can cover the value of delta H, that would make delta G positive. Suddenly, the same process that used to be spontaneous becomes non-spontaneous if temperature goes up. So we got yourself an interesting process. This process actually is dependent on the temperature. A very good example will be the mass production of ammonia. From thermodynamic analysis, we realize that this reaction generates a lot of heat. Okay, so this reaction is exothermic, but with the 4 moles of gas, you only want of 2 moles, so the delta S of the reaction decreases. And we have this reaction that is temperature dependent. So in engineering, we specifically choose something right here. So we raise the temperature of this reaction on purpose to make this reaction non-spontaneous. Since it's a non-spontaneous, reaction can stop at any time. for example, by cutting down the nitrogen or hydrogen. This way, they give us extra safety precaution for mass production of ammonia. Remember, in chemical engineering, those chemical engineers prefer the reaction that they can control. For the reaction that's spontaneous, that is not something they can control, because it's going to be on or by their own or by its own. So those chemical engineers has nothing to control it. And if things are out of control, we got an accident. So I just want you guys to realize there's a difference between chemistry and chemical engineering. Okay. Although we used to joke about that we do not like each other, but we do work each other, and we work the same equation, chemical equation, from different point of view. Our fourth case is where delta H is greater than 0, delta S is greater than 0. If delta S is greater than 0, negative delta S is less than 0. And just like we have discussed before, negative delta S is less than 0. And if we have T that is small, and this process becomes non-spontaneous, because there's still more of a positive delta H left. As the temperature goes higher, T times negative delta S becomes more and more negative, then that will take care of this delta H, make delta G negative. So again, this is another scenario where we can see the reaction is spontaneous depending on the temperature. And then only this time, the reaction is spontaneous at higher temperature. A very good example would be the decomposition of a mercury oxide. The mercury oxide is what we called red sand. And the ancient Egyptian, back in 4,000 or 5,000 years ago, they collected those red sands because those red sands are very stable at room temperature. In other words, the forward reaction is not spontaneous. Only it becomes true if we heat up this compound. At higher temperature, the forward reaction becomes spontaneous. Then we can get mercury out. And back in the old days, those nobles used mercury as a mirror to powder their noses. So there's some fairy tale about chemistry based on those 4 different cases. But from the last 2 combinations, we realize we do have a process that depends on temperature. If we have delta H and delta S, both on the same sign. All right. Now that we understand we can have a certain process that is temperature dependent, and we need to know what is the temperature that can make the reaction spontaneous or make it non-spontaneous. So here we're going to use delta H and delta S both positive as an example. Remember that we discussed if we have delta H, delta S both in the same sign, the process is temperature dependent. In this diagram, we see that delta H is greater than 0, so that's why the line here is a delta H that's greater than 0. Delta S is greater than 0 because because delta S here is the slope of this yellow line, oh, I'm sorry, the blue line, because as you can see, the x-axis is the temperature, so delta S is a slope, it's a positive, delta S is positive. And we can see that these two lines cross at a certain point where those delta H and T times delta S both have the same value. According to the subtraction, delta H minus T times delta S, if they have the same value, delta G is equal to 0. So this is where we see the delta G equals to 0. The two lines cross each other. So at this cross point, the point of the crossover, we can actually find out what temperature is. This temperature is called crossover temperature. At this temperature, delta G equals to 0. So how are we going to get the crossover temperature? We add T times T crossover times delta S on both sides, then divide both sides of the equation by delta S. So we have T times T crossover equals to delta H over or divided by the delta S. So from this equation, we understand if both delta H and delta S have the same sign, the crossover temperature is positive, right? If we have negative delta H, negative delta S, we still want a positive crossover temperature. But what happens if we have the process where delta H and delta S have a different sign? And remember, this process is what we call temperature independent. So let's pick. Delta H is a positive, delta S is a negative. Positive divided by the value negative, we wind up with negative value of temperature. What does that mean? We understand that temperature can only be negative, right, in a unit of Kelvin. So if we have the negative temperature crossover temperature, that means temperature is not important. Also means this process is temperature independent. So if we wind up with a negative T crossover, we will know this process is temperature independent. This is something I just want to let you know in case you're confused about which process is temperature dependent or temperature independent. You can actually calculate the T crossover. If it's positive, temperature dependent, negative, temperature independent. All right, now let's take a look at an example. We've got this reaction, copper 1 oxide react with carbon so that we can have a pure copper out. At 298 Kelvin, which is 25 degrees, delta H is equal to 58.1 kilojoules. Delta S is equal to 165 joules per Kelvin. Two questions. Use the data that are provided to decide if this reaction is spontaneous at 25 degrees and predict how delta G will change with increasing temperature. Second question is that with the assumption of delta H and delta S both constant with the temperature, that means independent of temperature, what is the temperature at which the reaction becomes spontaneous? From the second question, we know pretty much already that this reaction is temperature dependent. Well, let's see. Remember, delta G equals to delta H minus T times delta S, and the T must be in Kelvin, so we convert 25 degrees into the Kelvin by adding 273 to it. We have a delta H that is 58.1 kilojoules, delta S equal to 165 joules per Kelvin. Both delta H, delta S have the same sign, which is positive. All right, delta G equals to delta H minus T times delta S. So we got the delta H here, and we got the T and the delta S right here. But here, I would like you guys to notice that we got two different units in energy. That is the mistake I made all the time when I was an undergraduate student. We cannot carry out this calculation as is because we have two different units of energy. We must put them into the same unit. So that is why we need a conversion kilojoules to joules or vice versa. So we wind up with a positive 8.93 kilojoules. Without that conversion, you may wind up with negative. So we realize this is spontaneous. And with that wrong information, we got our conclusion wrong. So please be very careful, very, very careful about the difference in units between delta S and delta H. Because delta H is usually kilojoules, while delta S has joules as part of its unit. Delta G is greater than 0, so we understand that this reaction is not spontaneous, meaning the forward reaction is not spontaneous. Reversed one actually is. Is this reaction temperature dependent? Yes. How? Because delta H and delta S have the same sign. Since they're both positive, we understand that as temperature increases, we got the more and more value with a negative sign. That will definitely take care of the delta H to make delta G negative. So delta G will decrease as temperature increases. But to what point? So we can calculate the T crossover by having delta H divided by the delta S. Again, kilojoules divided by joules. So we have to convert the kilojoules to the joules by putting 10 to the third to the value, and we figure out it's 352 Kelvin. So if we subtract the 352 by 273, we find out the temperature is somewhere around 80 degrees. That means just simply heat it up a little bit, and this reaction is reversed. So forward reaction becomes favorable. Just like delta H and delta S, we can put a standard free energy by having 0 on the subscript of the right of this delta G. That means the free energy of a substance at its most stable form at 298 Kelvin. Two methods that can reach us the same goal, delta G0 of the reaction. First, we can use the second law of thermodynamics if we know the delta H0 of the reaction and the delta S0 of the reaction. Or we can use Hess's law if we know delta G0 of F. What is the delta G0 F? It is called the standard free energy of formation. And that means the free energy of formation of 1 mole of substance from its constituent element under the standard state condition, kind of like a delta G0F, standard heat formation of a pure substance, of a compound. It has the unit as kilojoules per mole for delta G0F. And I want you guys to watch out the unit for delta G0 there is kilojoules. So there's some difference there. If we have a free element, remember delta H0 is 0 for formation of a free element. And we have that too. So we said for free element, delta G0F is equal to 0. The sign of delta G0 actually tells us which direction of the reaction is favored, right? And if it's negative, that means formation direction is spontaneous because delta G less than 0. Compound is more stable than its elemental form. If it is a positive, so we understand the formation direction is non-spontaneous, reverse point is. Compound becomes unstable and is subject to decompose in theory. So here, two mathematics equations that I want you guys to realize in order to calculate delta G0 of the reaction. We can have approach of a second law of thermodynamics, and we can have the Hass's law if we know the standard free energy of formation of the substances. Now let's practice this two equations with this example. We have the compound called potassium chloride, KClO3, as the oxidizing agent in the firework that undergoes a solid state, oh my god, disproportionation reaction when heated. So this is some word that is very interesting, two TIONs. Alright, so apparently this equation has been taken care of. I find out that this equation is balanced. First question, if we are given delta H0 formation of each substance and S0 of each substance as well, can we calculate the delta G0 of the system or the delta G0 of the reaction at 25 degrees? Or if you are given delta G0 of each substance, can we figure out the delta G0 of the reaction? And I'm interested to see how consistent these two values are to each other. Question C here is see whether this reaction is spontaneous at 35 degrees. And question D, however, is a little bit confusing. Does the reverse reaction become spontaneous at a high temperature? What is temperature if it does? Of course, assuming that delta H0 and delta S0 are constant with the temperature, that means they do not change over the temperature. Alright, so now let's answer our first question. We have delta H0Fs of everything, and we also have delta S0 of everything. What we can do here is to calculate delta H0 of the reaction as well as the delta S0 of the reaction. Then we can use second law of thermodynamics, that equation to calculate what the delta G0 of the reaction is. As reactions is balanced, so we can use the Hass's law with the delta H0F and the delta, so the S0 of the substance. So we start with the product. So we have 3 moles. So here comes the 3 moles. 1 mole, so that's 1 mole. And this is 4 moles, so that's 4 moles. Remember, product minus the reactant. We have negative 144.3 kilojoules. That is for the standard heat of the reaction. The standard entropy change of the reaction, and we follow the same formula, but this time we use entropy instead. Product minus the reactant, so we have negative 36.8 joules per Kelvin. Remember, delta G have the same unit as delta H usually, so I would like to convert the joules per Kelvin into kilojoules per Kelvin before I forget. According to second law of thermodynamics, delta G 0 of the reaction is equal to delta H 0 of the reaction minus T times delta S 0 of the reaction. We put the numbers in, so we got a negative 1.133 kilojoules. All right, so this is delta G0 we get from H and S, the enthalpy and entropies. If you are given the standard free energy of formation of each substance, we can directly use Hess's law to have the delta G0 reaction figure it out. And it gives us negative 134 kilojoules. 133, 134. I would say they are consistent. Because remember, last digit is a second digit. That is good enough for me. I'm sorry. Okay, so equations that I want you guys to get familiar with. The equations from Hess's law, the equation from the second law of thermodynamics. Now let's look at question C. C wants to know whether this reaction is spontaneous at 25 degrees. If you recall, delta G of this reaction is negative 134 kilojoules. That's less than 0, meaning this reaction is spontaneous at 25 degrees. It is spontaneous, but would that reaction happen easily? Of course not. By checking out the sign of delta H0 and delta S0 of the reaction, we find out that they're both less than 0, meaning this reaction is temperature dependent and the reaction becomes non-spontaneous at a higher temperature. So yes, the reaction is spontaneous at low temperature, but it becomes non-spontaneous at high temperature. Now certainly question D makes sense. The question wants to know whether the reverse of the reaction becomes spontaneous at a higher temperature. So here we go. We have the reverse of reaction. So this time potassium chlorate has become as the product. Okay, so since the reaction is reversed, we change the sign of our functions, so state functions. The delta H used to be negative, now becomes positive. Delta S of the reaction is negative, now it is positive. And of course, we can calculate the crossover temperature since both delta H0 and delta S0 have the same sign. And it tells us it's a 3,920 kelvins. This is how the temperature, so what the temperature is when the process becomes spontaneous. Alright, as we move to the end of this chapter, we finally try to connect the equilibrium constant with something in thermodynamics. It could be delta H, it could be delta G, it could be delta S. Remember, this is something that we pointed out at the very beginning of this lecture of this chapter. However, I just want to go through some kind of a derivation using logic to derive the connection between the KEQ, the equilibrium constant, with the free energy. So now we realize it is not delta H, it is not a delta S, it is a delta G that we want to pin with. Come to think of it, it makes sense because delta G is the only state function tells us whether a reaction is spontaneous or not. And then K is the measure of how spontaneous the reaction is. So K tells us the degree of spontaneity of the reaction. So for example, if K is greater than 1, so we understand the reaction is spontaneous moving forward. If K equal less than 1, we understand reaction is not so spontaneous because K equal less than 1. So it is pretty much more favored to the reverse side. So this is something that we have already discussed long before. Okay. I believe some similar discussion has occurred in Chapter 15 when we talk about magnitude of KEQ. So here we attempt to combine the KEQ with the reaction quotient and try to get this connected with delta G. If we recall from Chapter 15, when we learned the reaction quotient, we said if a reaction quotient is less than KEQ, reaction proceeds to the product. And of course, from our method, if we put a Q in the first followed by KEQ, if we draw the arrow from small to the large, it's going right, so going to the product side. So reaction proceeds to the product. And if Q greater than KEQ, we understand the arrow is going to be to the left. So that means the reaction proceeds to the reactant, shifted to the left. But I would like to rephrase those statements. Reaction proceeds to the product. I would say the forward reaction is spontaneous because it's going in that direction. If a reaction proceeds to the reactant, I would like to say forward reaction is non-spontaneous because the other direction is spontaneous, indicated by the Le Chatelier's principle, right? If Q equals to KEQ, the reaction is at equilibrium. Okay. I got the two variables in that equation format. I do not like this. I would like one variable or combination of variable on one side, the value on the other. So the simpler way for me to do it is we take a division, right? So if we divide Q by the KEQ, so the first Q less than KEQ, meaning the division leaves the value that's less than 1. This is the reaction that forward direction becomes spontaneous. So the forward reaction is spontaneous. Remember, if it is spontaneous, delta G must be less than 0. Now we start to see less than 1, less than 0. We start to see some pattern here. If Q is greater than KEQ, meaning the quotient is greater than 1, and since the forward reaction is non-spontaneous, delta G must be greater than 0. Less, greater. We definitely see some pattern. If Q over KEQ equals to 1, which is Q equals to KEQ, reactions at equilibrium. Now we have equal. But the thing we do not like is we got a 1 instead of a 0. When we try to draw the linear relationship, we do not want the intercept. In other words, we want those 1 become 0. Just what kind of mathematical operation we can apply on this quotient so we can have 0 in the result. Of course, you can tell me -1, right? This quotient -1, and then so we have a 0 greater than 0 equals to 0. But this is not the mathematical operation we're looking for, because we want a single step. We do not want just -1 because we do not want the, like I said, the intersection when we draw the linear relation. So what kind of operation we can apply on this quotient. So we can get the 0 out of 1. In other words, what operation we can apply on 1 except for subtraction to make that value to 0. You're right, log. So if we take a log of this quotient, log of 1 equals to 0, equals to 0, equals to 0. That is good. But now we just want to know. So I'd like to put a circle around, just let you know it's not greater than or equal or less than or equal. So now let's see if we put a log in front of Q over KEQ to see whether they still keep the same sign here. If we have a quotient that's greater than 1, after we take the log, the value is greater than 0. The value less than 1, the log must be negative. Now we realize that if we take the log, it's less than 0, delta G less than 0. The log that's greater than 0, delta G is greater than 0. If the log equals to 0, delta G equals to 0. That is perfect for us to draw the conclusion that the delta G is directly proportional to the log of Q over KEQ. Oh, I'm sorry, so this is something that popped out. All right. Now that we have delta G that is directly proportional to the log of Q over KEQ, our next step is try to have this directly proportional with the equal sign. Before we do anything else, I would like to remind you, over the time, I kept saying K is the function of temperature. But in this mathematic, I cannot say equation expression, I do not see temperature anyway. From the statement, temperature must be the part of the equation. So we have two choices to put the temperature. You can put a temperature that's multiplied by the delta G, or temperature that's temperature as the bottom of this division. Delta G divided by the temperature. What we're going to do here is to see just what a unit of A is. Actually, we just hope that the unit of A will remind us something that makes sense. Anything after we take the log become no unit. So that means the unit of A is determined by what the unit we have on the left. Remember that temperature has a unit of Kelvin. Delta G has the unit kilojoules per mole of the reaction. So the A has a unit joules times Kelvin per mole. This is the unit that's we are not familiar with. Well, let's set this aside to take a look at what happens if we have a delta G divided by temperature. Again, delta G is joules per mole, right? So there's a kilojoules, but we prefer to use joules. It's a joules per mole per Kelvin. That is the unit that we have seen before. The unit of universal gas constant. Suddenly, it's all cleared out. A is universal gas constant. If we multiply temperature on both sides, we got that delta G equals to RT log of Q over KEQ. That is one powerful equation. Why it is powerful? Because this equation has a lot of things all in that equation. Reaction quotient, that is something related to the initial condition. Equilibrium constant, temperature, and free energy. So 4 pieces of information all combined or mixed in that equation. And of course, according to the math here, log of a division equals the subtraction of the log. So we separate them out. So we have delta G equals to RT log of Q minus RT log of KEQ. We're going to put a little bit more math in this. Say if we have a standard condition. The standard condition tells us the initial concentration of all substances must be 1 molar. The initial pressure of all gases must be 1 atm, meaning there's going to be 1 with a certain power, all multiplied, all divided by 1 with any power is equal to 1. 1 multiplied by 1 is equal to 1. 1 divided by 1 equals to 1, meaning Q equals to 1. If Q equals to 1, log of Q equals to 0. If log of Q equals to 0, we have delta G equals to negative RT log of KEQ. And because we're talking about a standard condition, delta G becomes delta G 0, because 0 is a mark to label the condition. This is a standard condition. This equation, however, is one of the fundamental equations for thermodynamics, because that equation tells us how we can get a value of KEQ if we have standard molar free energy of the reaction, delta G0. And of course, we can have a way to calculate the delta G0 with the information we have. And it is possible. And in order to get a KEQ, so we have E powered by negative delta G over RT. And of course, that equation sounds familiar as well. Of course, we can get another equation of delta G for the non-standard condition. And since the second part, negative RT log of KEQ, can be replaced by delta G0, so delta G equals to delta G0 plus RT log of Q. So there are a lot of equations that we have just talked about, but the mother equation of all is this: delta G equals to RT times log of Q over KEQ. Because we can actually derive the rest of the equation from that equation. But it would become handy if we can just simply memorize all 4 of them. All right, the last example of the chapter. So here I just try to interesting you with the certain thing that in biology. So the key step of the metabolism of glucose for energy is the isomerization of glucose 6-phosphate to the fructose 6-phosphate. So G6P to F6P. And these two becomes an equilibrium. And the K for such equilibrium is 0.510 at 298 Kelvin. So we know the K. Do we know the delta G0? Sure, because delta G0 equals negative RT times log of K. Plug those numbers in. Make sure that the value of R must be 8.314. So we have positive 1,668 joules per mole. Is the forward reaction spontaneous? No, because delta G is positive. Now we are asked to calculate delta G when Q the reaction quotient for this reaction equals to 10. Remember, reaction quotient, that means product minus divided by the reactant. So F6P divided by the G6P. I'm sorry, so that should be ratio, not a ratio. Which equation should we take to get this job done? Delta G equals delta G0 plus RT log of Q, because we just figured out what delta G0 is. Okay, so we plug those numbers in. We know that delta G0 is, this is R, this is T, this is Q. And we find out it becomes more positive. If delta G becomes more positive, meaning forward direction is no longer spontaneous, which also means the reverse reaction is spontaneous. Remember, we have Le Chatelier's principle. So let's check that result with Le Chatelier's principle to see whether these two consistent with each other or match with each other. According to Le Chatelier's principle, remember, Q is 10, right? K is 0.5. So if you list the Q in the first place, draw an arrow from small, which is K, to the large. This is the direction. So this is the direction of equilibrium shifts. We understand equilibrium shifts to the left. Equilibrium shifts to the left, meaning reverse reaction is spontaneous. Now this line of calculation also takes care of Le Chatelier's principle, this calculation of delta G. So that is the reason why I said delta G, this equation, is one of the most powerful equations in thermodynamics, because now not only covers Q, K, T, temperature, and delta G, the spontaneity of the process, and also it got the Le Chatelier's principle covered as well. All right, question C here is we want to get the delta G if Q now is not 10 but 0.1. Put the numbers into the calculation, we find out now we have this reaction reversed, right? So the reaction, the forward reaction under this condition now becomes spontaneous. What is Le Chatelier's principle tells us? Q is now less than K. The arrow indicating the forward reaction is spontaneous. Throughout this calculation, I just want you guys to realize in our body or in any body of animal, the conduct of metabolism, this process can be controlled by the concentration of these two substances. If the body does not want this reaction to going forward, it can do that by accumulating concentration of F6P high enough so it will block this reaction. If our body wants the reaction to go forward, one thing we can do here, our body can do, is decrease the concentration of F6P. Of course, for the rest of the step of reactions in the metabolism circle. So with the lower concentration, equilibrium shifts to the right, so more G6P is converted to the F6P. So as you may probably already know in biology, there's two ways to control the reaction. First, concentration. Second, inhibitor. Right? So that is the chemistry mechanism to control the biological reaction by adjusting concentrations of the reactant and product. Well, enough of biochemistry. So now let's look at the last question. So here we're going to calculate Q if we know what the delta G is. First thing first, we need to convert delta G from kilojoules per mole to joules per mole. Same equation. Now we're going to calculate the Q. We know the delta G, and we know delta G0. R and T are also the ones that we know the value with, so we can calculate the log of Q. And we just E it so that we can get the value of Q, which is 0.186. Now let's look at this equation, delta G0 equals to negative RT times log of KEQ. This equation is one of the most important equations in thermodynamics, because that equation tells us just how the spontaneity of the reaction is going to be and what kind of a measure we can get to prove it, or just how K respond for the spontaneity of the reaction. If delta G0 less than 0, that means log of K must be greater than 0. So K must have a value greater than 1, such equilibrium. Okay. So such a reaction is going on forward because delta G0 is less than 0. So spontaneous reaction is spontaneous. So equilibrium mixture is mainly product. And that matches the discussion we had early on in chapter 16 and say if KQ is a larger value, so the product is dominant. If K less than 1, we understand that the reaction is not a spontaneous in forward direction. So actually the equilibrium is favored to the reverse direction, meaning reversed one is spontaneous. The equilibrium mixture is many reactants. For delta G, that's greater than 0. If delta G0 equal to 0, that means everything is at equilibrium and it's going to be the standard state. All right. If you look at the delta G equation, okay, which is negative RT log of KEQ plus RT log of Q. So here I play around these two terms so that I try to make a point here. The delta G, remember I said that this is the most powerful equation. Not only it covers those variables, also it takes care of Le Chatelier's principle. And from this equation, we understand from mathematics about why the equilibrium is plausible, meaning that equilibrium occurs automatically. Okay, so now let's look at this curve. So say if we have a pure reactant here at the very beginning, what is the value of Q? Remember, pure reactants, no product yet. Q has the formula of product concentration divided by the reactant concentration. Without any concentration for product, Q equals to 0. If Q equals to 0, the second term is out. With the forward direction, that means KEQ greater than 1, so log of KEQ is positive. Positive multiplied by negative RT make a delta G less than 0. So the forward direction is spontaneous. So it keeps on going, but it won't go to all the way to the product. The reason for that is if we have a pure product at the end, reaction quotient is infinity because product divided by the reactant. Now that we do not have any reactant, non-zero value divided by 0, Q is infinity. If Q is an infinity, this term becomes positive, a lot more positive than any other value that we can have as a negative from the first. In this case, delta G is positive. If delta G is positive, reverse reaction, right, is favored or spontaneous. So somewhere here in the middle of the reaction, we have equilibrium established. We have a little bit of everything, including reactants and products. So this is what equilibrium is for. And you may wonder why KEQ has to be greater than 1. How about KEQ less than 1? If KEQ less than 1, of course, we just flip this graph over, right? So if we have a pure product, okay, so the KEQ, if we want the reverse reaction, so KEQ is equal to 0, so it's going down, but we still have the same argument if we have a pure product there, so it's going back. So here is the point where we can have the equilibrium for this reaction. Same reaction, but in the reverse direction. So that the delta G equals to negative RT of log of K plus RT log of Q, or delta G equals to RT log of Q over KEQ is the most powerful equation. So I want you guys to understand, to memorize this equation, because this is the equation of all equation. We can derive delta G0 from this equation, and we can calculate KEQ from this equation, and later on we're going to see the same equation again in chapter 19 when we talk about electrochemistry. All right, another point I'd like to make about this delta G0 equation is it looks very similar with the other equation. For example, CC equation, okay, Clausius-Clapeyron equation for the heat of vaporization. It is negative RT log of PVAP. From Arrhenius equation, we understand EA is negative RT of log of K. And of course, in our chapter, delta G0 equals negative RT log of something, log of KEQ. Now we see negative log of negative RT times log, negative RT times log. So why the similarity? Why are they the same? Even though we understand they constitute the basic foundation of modern physical chemistry. Because we use the same theory to explain all of it, which is KMT theory. Okay, so kinetic molecular equation, so theory. This theory tells us those particles are in a gas, but they just have a different energy to perform. Remember, delta H is the energy as well. So delta H, delta G, and EA, they all the energy terms. So we just use KMT with the different of energy to explain the chemistry, the chemical reactions. That is end for chapter 18. And in this second half of lecture, we focus on the Gibbs free energy. And we understand the delta G actually tells us whether the process is spontaneous or not. Okay, if we have a spontaneous process, delta G must be less than 0. Less than 0, not greater than 0. Okay, so it's less than 0. And throughout a set of calculations, so we realize that we can calculate the delta G0 with two different approaches. We can calculate it if we have delta G0F, standard free energy of formation of substances using Hess's law, or we can use the second law of thermodynamics, delta H0 of reaction minus delta S0 of the reaction to have the value of delta G0 figure it out. Once we have delta G0 figured out, we know what KEQ we're looking for. From that KEQ, so we know just how good this reaction is going to be. And also, whether we need to put external energy to have this reaction to take place. If the reaction is not spontaneous in forward direction or in the direction we expect. Okay, so that is it for the chapter 18, and I will definitely assign some of the homework to you guys, and I see you guys in chapter 19.